Everybody. All right, you guys, for being right on time. I appreciate that. All right. Anybody have any questions? Josiah.
Can I do the periodic table song next week? Because I think I did it.
I'm sorry, what?
Can I do the song next week? Because I think I memorized it.
Yeah. Do you want to do it now, or you want one more week?
I think I can maybe do it now. Let me see. Yeah, I think I can.
All right. If you want to wait another week, you can do that.
I think I'll just do it now.
All right, go ahead.
And what I'll do is I'll even close my eyes that way. There's no way.
Okay. Yeah. Sometimes it helps to do that.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, then oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times, magnesium, aluminium, silicon, phosphorus, then sulfur, chlorine, and argon, potassium and calcium so you'll go strong, scandium, titanium, vanadium, and chromium, and manganese. And then I think I'll just skip the chorus because that.
Okay.
Iron is the 26th, and cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine, film of krypton helps light up your room, radium, and strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silverware, then cadmium, and indium, tin cans, antimony, and tellurium, and iodine, and xenine, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, olium, erbium, thallium, terbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, then lead, bismuth for your tummy, polonium, acetine, winapium, radon, francium will last a little time, radium, then actinide to 89. And I'll skip the course again. Actinium, thorium, protactinium, uranium, neptunium, plutonium. This is where I got stuck for a bit. Americium, curium, berkelium, californium, einsteinium, fermium, Mendel. Wait a minute. Americium, curium, berkelium, californium, einsteinium, fermium, mendelvium. Wait a minute. Fermium, mendelvium, nobelium, lawrencium, rutherfordium, dubnium, seaborgium, bohrium, acium, metnerium, durstedium, organium, copernicium, nihonium, flerovium, Moscovium, Livermorium, Tennessean, and Oganescent.
All right. Well done, everybody. Round of applause for Josiah. That's impressive, Josiah. Very good in a week, too. Awesome. All right. Extra credit points for Josiah. All right, Richmond.
So I heard somewhere that you could make gold out of coal by using a nuclear reactor.
Theoretically. People have been trying to make gold since Rumpelstiltskin's days, right? Spinning it out of straw. Theoretically, we can change one element into another element. Gold has not been that, as far as I know, no one's been successful at doing that yet. Zane.
Actually, somebody has. Somebody's turned mercury reactor.
Well,
of course, it is very expensive. The rate isn't good at all. You wouldn't make any money.
No, and it's not a foolproof kind of a thing.
I agree with that. We have made gold.
All right, excellent. All right, well, once again, Josiah, very, very well done. That was that. Actually, I could understand you a lot better than I could understand the video. So that was helpful. You went a little bit more slowly. So that was awesome. That was really perfect. Yeah, like everybody's saying, very impressive. All right, so anybody else wants that extra credit, feel free. Oh, they have a lyric sheet on YouTube. That's helpful. Yeah. All right, Arhan. Is your hand up, Arhan?
Try the Satan the periodic table song.
Oh, are you ready to do it this week?
Yes, but I need to go to the restroom, so I'll be back in a minute.
Okay, why don't we do it? Why don't we plan on you doing it next week, Arhan? That'll give you another week to practice anyway.
Okay.
Okay, that sounds great. We'll do that. All right, Arhan next week. Okay, writing my notes. All right, perfect. All right, let's go ahead. Zane, your hand is still up. All right, I'm going to go ahead and share my screen with you guys so we can get ready for a big class today. We have a lot of stuff that we're going to do today. Zane, is your hand still up on purpose? If you could lower it, that would be great if you're done. All right, I'll just lower it for you. There we go. Okay, so last week and yesterday, you guys read about the different kinds of
can't
chemical
hear it.
bonds. And this week, we're going to learn about different kinds of chemical reactions. So this is all really important. So I want to review bonds today and then do a little bit of an introduction into chemical reactions. So I have a couple jokes for you first, or cartoons rather. I like this one. Seriously, dude, I think you're overreacting. Overreacting. Don't you feel like you do that sometimes? Steam comes out of your head. All right, look at this one. What is the chemical formula for banana? Josiah.
Isn't it just K?
No, that would be potassium. There's a lot of potassium in a banana, but there's a lot more than just potassium. And remember, this is a joke. Banana squared. two nas in that. All right, how about this one? Did you hear about the chemist reading a book about helium? He just couldn't put it down. And what are your teacher's favorite elements? They are carbon, hydrogen, oxygen, cobalt, lanthanum, and tellurium. Chocolate. Arhan. Oh, okay, your hand was up. All right. Chemistry puns. I'm in my element. In my element. All right. So we all know that matter, all matter in the universe is made out of these tiny particles called atoms. And an atom has a center that's called the nucleus. What's in the nucleus of an atom? Josiah.
Protons and neutrons.
Protons and neutrons. So protons have a positive charge, neutrons have no charge at all, an ought charge, and they are in the nucleus. Excellent. What's moving around the outside of the nucleus? Charlotte. Oh, I think go ahead.
Electrons.
Yeah, electrons, which have a negative charge, are moving around the outside. So what is this outermost shell called? And remember that electrons have their atoms have their electrons in these energy levels that we call shells. What's the outside energy level or the outside shell called? It's really important. So it has its own name. Mel.
The valence electron
Yes,
shell.
yes. The outermost shell is called the valence shell or the valence electron shell. And it's those valence electrons that interact with other things. So atoms want to have a certain number of electrons in their valence shell. How many do they want to have? Josiah.
8 or none.
They want to have 8, or they really want to have 8. Once they get rid of what's in their outside one, for the most part, they're still going to have 8 in the one below that. But they either want to have 8 or none. So we call that the octet rule. We can sum the octet rule up this way. I want 8, right? Electrons have a bad attitude, or atoms have a bad attitude. They want 8 or none. So we say that if a valence shell, this outside shell here, is full, it has 8 electrons in it. So take a look at your periodic table and tell me, name an element that has a full valence shell. Mel.
Neon.
Neon. Name another one. Mina.
Argon.
Argon, keep going. Shout them out.
Organoson.
All right.
Helium.
Helium,
Radon.
radon,
Krypton.
Xenon.
krypton. There you go. Basically, the noble gases. The noble gases have a full valence shell. Now, depending on where they are on the periodic table, we can tell how many electrons they have in that valence shell. And that's pretty cool. All right, let's look at this now. What do we call this kind of structure? Each of those colors is an atom. What do we call it when atoms stick together to other atoms? What are they forming? Mel.
Bonds.
So that's the gray lines in between are bonds. But what do we call this whole thing?
Molecules.
Messiah. Yeah, we call it a molecule. So the spheres in the picture represent atoms, and the whole thing itself is called a molecule. Now, there are a couple more terms that we need to make sure that we understand. We need to know the difference between a compound and a mixture. So a compound is anything that can be formed when we chemically combine two or more elements together. Basically, a molecule is going to be a compound for the most part. Mixtures are things that we make by mixing. So mixtures are mixed, compounds are bonded. Okay, that's a quick way to remember that. Mixtures are mixed together. If you've got big chunks of stuff that are separate, you can see the individual pieces like that. That's called heterogeneous. If they're all sort of blended together, that's called homogeneous. And then a compound has those bonds. So back to this molecule here. Remember that the atoms in the molecule, all these individual colors, they all stick together with bonds. And those lines in between the balls represent the bonds. Now, atoms might be connected by strong bonds and stick together really tightly, or they might form temporary, really weak bonds with other atoms that they just bump into. Sometimes they can do that. Now, both the strong bonds that hold them together and the weak ones that are weaker, they're going to create these connections that are important in the chemistry of life. So there, it's important to understand about bonds. Now, there's 4 different kinds of chemical bonds that we can form. We'll talk about the first 3 first, and then the last one. So the 4 kinds of bonds are, anybody name one? Name a kind of a bond. Zane.
Ionic bond.
Ionic is one of them. Michaela.
Covalent.
Covalent. That's 2. Josiah.
Metallic.
Metallic. And then number 4. Mel.
Hydrogen.
Hydrogen. Those are the 4 kinds of bonds that we can form. So we have to remember what an ion is. An ion gave something away or it gained something. What did it either give away or gain? Zane.
A proton.
Not a proton. If an atom gives away or gains a proton, it becomes a completely different atom, right? If it's carbon and it gains a proton, it becomes nitrogen. If it's nitrogen and it loses a proton, it becomes carbon. So it's not a proton. Protons stay put. Protons have to stay in the nucleus, have to stay in the same amount, or the element changes altogether. Ari.
A valence electron.
It gives away a valence electron. Excellent. So it either gives 1 or 2 or 3 or gains a couple. All right. So an ion is an atom that either gave away or gained 1 or more electrons. Now, remember, electrons have that negative charge. Whenever you think of electron, picture a little e with a line, like for a negative sign. That's how they represent electrons when they write them down. The little e with the negative sign. That helps you remember that electrons are negatively charged. So if I give away something negative, that leaves me a little bit positive. If I gain something negative, that leaves me a little bit negative. So when an atom gives an electron away, it's now positive, and it's a kind of an ion. What kind of an ion is it? Well, there's 2 kinds of ions. Josiah.
The cation.
It's a cation. Here, I got another cute way for you to remember. A cation is positively charged. Positively charged. All right, now take a look at your periodic table. Which side of the periodic table is likely to form cations? The left or the right? Josiah.
The left, specifically
Yes.
alkali metals.
Yes, the alkali and alkaline earth metals are really likely to form a cation because they want to give away one or more electrons. So they want to give away negative, so they want to become positive. They want to form cations because it takes a lot less energy to give 1 or 2 away than it does to gain 6 or 7, right? All right, here's another little cartoon. I think I've lost an electron. In fact, I'm positive. So is this a cation or an anion? Mel,
A cation.
this is a cation. Excellent. It is positive. Now, when an atom gains an electron, now it's negative. It just gained that little e with the minus. It gained something negative. So it is an anion. So in this picture here, the cation is sodium and the anion is chlorine. And now, once the sodium has given its electron away, it's less negative, it's positive, it's a cation. And the chlorine gained a negative, so it's a little more negative now, it is an anion. All right, now, you can see that here. We've got an ion. We have 2 ions that are being formed here. The bonds between ions are called ionic bonds. That's pretty easy. Ions form ionic bonds. The cation, in this case, that's sodium, gives its electron away, or it did. The anion takes it. Now, since they both have an electrical charge, they're going to stick together like 2 magnets. So the resulting compound is going to be considered neutral because it has both the positive charge from the cation and the negative charge from the anion. Negative charges mathematically cancel each other out. So take a look here in an ionic bond. There they are. There are the 2 individual atoms. One gives the other away. Now, the sodium has a positive charge. The fluorine has a negative charge. They're not bonded to each other. They're not glued together. They're just stuck together kind of like magnets. Now, that doesn't mean they're not strong. In fact, they're very, very strong. In fact, they're stronger than any other kind of bond. Ionic bonds are really, really strong. There is a complete transfer of electrons. That makes them very, very strong. So ionic bonds are very strong. They are the attraction between atoms that have opposite electrical charges. Think of an ionic bond as being a really strong magnet, and pulling that magnet apart is really hard to do. Here's another cute cartoon for you. 2 atoms talking together. I'm about to lose an electron. Are you sure? I'm positive. And I love this. I want this shirt. Name's Bond. Ionic bond. Taken, not shared. And look at this one now. See those dots around there? We'll talk about those in just a second. But here's an atom that has 7 in its outer shell. And here's an atom that has 1. Here, sir, this is all I have. Wow, I feel so positive. All right, now there are, and now I want to talk about covalent bonds. So that's ionic. Ionic is a complete transfer. When in an ionic bond, one atom gives its electrons or electron to another atom, and that one takes it. They're now charged differently, so they stick together. All right, a covalent bond is different. So here in this picture, we have 2 girls, and they both need a blanket. It would not work for one girl to give the blanket to the other girl. The only way for them to be warm is to share that blanket. Atoms can do the same thing. They can share electrons, so they're both happy. Here, I can't get an electron from you, neither can I give you one. Let's just share. Remember that outermost electron energy level is called a valence shell. So when those atoms share one of the electrons in their valence shell, it's called covalent, right? It's the valence shell and they're cooperating. They're cooperating with their valence, covalent, sharing. In a covalent bond, electrons are shared between the atoms. Remember, both of these atoms want to be stable. They both want to be like a noble gas. Everybody wants to be a noble gas, but neither of them wants to give away one of their electrons. So they share, and that sharing makes them stable. It makes them happy. When they're happy and stable, they want to stick together. Now they stick together because they're sharing, but they're both holding on really tight. Like those girls with the blanket. They're both going to be holding on to that blanket really tight and keeping each other really close, really nearby. Sharing is caring, covalent bonding. All right, so let's look at these dots now. We talked about those dots in that little cartoon picture. There's a way that we can show how atoms bond together to make molecules by just using dots and symbols. So imagine this. Every atom has these electrons flying around in the electron cloud around it. The electrons are like little tiny friends that help atoms stick together. So those outer electrons, the valence electrons, they're the most important ones when it comes to bonding, when it comes to making friends with other atoms. They're the ones that we're concerned about. All right, so when we do what's called, we can create what's called an electron dot or a Lewis dot formation. So the very first thing we're going to do is write the symbol of the element like this, Cl. We're going to write that down. That represents chlorine. Now we have to figure out how many valence electrons chlorine has. So how many electrons does chlorine have altogether? It's right there on the slide. Lainey.
17.
It has 17 electrons, right? So we have to figure out where they go. So that very first shell, the very closest one, closest to the nucleus, it has room for 2. So the first 2 go there. Then the next one has room for 8. So 8 go there. That makes a total of 12. I'm sorry, 10, right? The 2 from here and the 8 from here, that's 10. So the third shell, it has room for 8, but how many does it have? Josiah.
Perfect.
Yeah, it has room for 8, but there are only 7 because 2 plus 8 is 10 plus 7 is 17. All right, so now that we know there are 7 electrons in the valence shell, we can draw them onto this symbol right here. And we can, that's a very useful tool that we have. So let's put them in. There's 2 and 2 more and 2 more. That's 6 and 1 more right there. Now, each of those dots stands for 1 valence electron. So there's 7. All right, now get out your pen and paper. Told you to bring pencil and paper to class today. Let's draw the symbol for carbon. Very first thing we're going to do is write the symbol of the element. So I want you to draw the C for carbon. Now look at your periodic table and tell me how many electrons carbon has. Mel.
6.
It has 6. How many can that innermost shell hold? Put your fingers up. 2. The innermost, for all of the elements, the innermost one holds at most 2. In hydrogen, it's going to hold 1, but 2 for everything but hydrogen. So we've got 2. So how many does that leave to be in the outer shell? Hold up your fingers. 4, exactly. Now we're going to draw our dots around this carbon, and we're going to draw them like this. 1, 2, 3, 4. All right, that's how we add those dots. You just made a Lewis dot diagram for the element carbon. And we can tell by looking at this, it has 4. Now, how many does it want to have? How many valence electrons does carbon want to have? 8. Yep, it wants to have 8 because remember the octet rule. I want 8. They all want to have 8 in that outer shell. So how many different bonds can carbon form? 4. Yeah, it can form 4. It can form 1 here and have 2 here, 1 here, 1 here, and 1 here. That ability of carbon to form all these different bonds with all these different chemicals is critical to life on Earth. It is so important. We have a whole unit just talking about the bonds that carbon makes. One whole unit of our class will be carbon chemistry. It's very cool. All right, now let's look at some of these and see how they can bond with hydrogen. So let's start with carbon right here. So carbon has 4 valence electrons and hydrogen has 1 valence electron. So look at your dots, 1, 2, 3, 4, 1. So how many hydrogens can bond with 1 carbon? Josiah?
4.
4. Let's look at them. There they are. 1, 2, 3, 4. That's what methane is. If you've ever heard of methane, so, you know, methane is a greenhouse gas. It's one of the major greenhouse gases that we have, keeps our planet warm. That's what methane is, CH4. 1 carbon, 4 hydrogens bonded just like that. All right, now let's look at the next one, nitrogen. How many valence electrons does nitrogen have? 5. Excellent. It has 5. So hydrogen has 1. So how many hydrogens can bond with 1 nitrogen? 3. Let's look at it. 1, 2, 3. This one's already full. See, that's already full right there. It wants 8, and it wants like 2 on each side. So we've got 2 there already. So 1, 2, 3 hydrogens can bond with that. That's ammonia. You might have smelled ammonia. Some people use ammonia to clean. So you might smell that. Yep. All right. What about oxygen? How many valence electrons does oxygen have? Let's see here. Ella.
4.
Not 4.
Oh, 6.
Yeah, it has 6 valence electrons. So since oxygen has 6 and hydrogen has 1, how many hydrogens can bond with 1 oxygen? Yes, 2. That makes water. That makes water. You can put 1 here and 1 here, and it actually ends up twisting a little bit like that. The molecule's a little bit off center like that. That's H2O. That's water. All right. Now, since hydrogen has 1, and hydrogen, how many can it bond with? Remember, hydrogen only has 1 electron. So yeah, I can only bond with 1 other one. You can have an H2 molecule. That's hydrogen gas. Remember, most of our elements are found in 2 or more in nature. So yeah, excellent, excellent. So you guys just made some bonds. You made some covalent bonds. They're covalent because they're sharing. Nobody gave anybody else their electron. Nobody took an electron. These are sharing with one another. Back to these girls again. We've got this sharing happening here. All right. So there are 2 types of covalent bonds. In one type, the atoms share those valence electrons equally. So that's like on the top. Sarah, I'm cold. I'm cold too. Wow, we both feel so cozy and comfortable after sharing the blanket. They're sharing equally. They're both nice and warm, sharing equally. In the other kind of covalent bond, one of them is a little bit more selfish, and it pulls those electrons a little bit tighter to itself, like in the bottom picture. They're sharing the blanket, but Sarah takes more of the blanket because she's feeling colder. We're both sharing the blanket and feeling comfortable, but Sarah is pulling the blanket more toward herself. Those are the 2 kinds of covalent bonds. Anybody remember what those 2 kinds are called? Josiah.
I think wasn't it like a polar bond? It's like there's the one that like it pulls it toward it.
Yeah. Yep. So here's a little cartoon picture that shows you. These are the 2 kinds of covalent bonds. There's polar covalent and non-polar covalent. So in a polar covalent bond, one of the atoms pulls the electrons a little bit closer to itself. So it's unequally shared. It's going to spend more time close to one atom than it does close to the other one. In a polar or non-polar covalent bond, like the one on the right, it's going to be equal sharing. They're going to spend their time around both atoms. Now, again, remember when we're looking at something like this, like let me go back to a better picture here. When we're looking at something like this, that does not mean that those atoms now they're holding still. Those electrons are constantly moving around the atoms, constantly. But when they're sharing, if they're shared equally, they're going to be constantly, in this case, moving around both equally. In this one, they're going to spend more time moving around the chlorine than they do the hydrogen, right? So non-polar covalent bonds, these right here, they're going to form between two atoms of the same element, or between atoms of different elements that share their electrons pretty equally. So oxygen is an example. Hydrogen gas is an example. Oxygen is just two oxygen molecules together. That's going to be a non-polar covalent. They're going to spend their time around both of them equally. Something like water, water is a polar covalent bond. In a water molecule, which is what we've got right here, oxygen and two hydrogens. In a water molecule, the bond that's connecting the oxygen to each hydrogen is a polar covalent bond. So you can kind of think of the oxygen molecule like a bully. It pulls those electrons harder than the little hydrogens do. So since it's pulling the electrons closer to itself, it is a little bit more negative. Since these are not keeping the electrons as close to themselves, they're a little bit positive. They have a partial positive charge. This has a partial negative charge. So we say that oxygen is more electronegative than hydrogen is. It shares, it attracts those electrons more strongly. So the oxygen part of water has that partially negative charge. That's pretty important because it's that little bit of negative in the oxygen and the little bit of positive in the hydrogens that allows one water molecule to stick to another water molecule. Now, molecular oxygen, like you breathe in, that's non-polar. They're shared equally. Got equal sharing, they're both happy. Now, sometimes we have a bond in which two atoms just share one pair of electrons. That's called a single covalent bond, right? Sometimes they share two pairs. That's called a double covalent bond. Sometimes they share three pairs, and that's called a triple covalent bond. And this is how we draw them right here. So a single has one line, a double has two, and a triple has three. So which do you think is the strongest? The single bond, the double bond, or the triple bond? Matt?
I actually was having a question about
okay,
the
go ahead.
bonds.
Go ahead.
So with that, couldn't there be a quadruple bond? Because in all they want of like with the octet rule, they want an outer shell of 4. Or I mean 8. If they have 4 valence electrons each, couldn't they share them and then have a full outer shell?
I'm looking it up. They're rare. Yeah, can happen, but they are rare. I've never encountered a thing that has one. I'm looking here to see what some of the transition metals, we don't talk too much about those transition metals. Those are ones in the middle of the periodic table. I told you that they're really complex, so we won't spend a lot of time with them. Theoretical calculations will show some triple bond or quadruple bonds and some quantum chemical investigate. We're getting into like college level advanced physics here, or advanced chemistry with quadruple bonds. Yes, they can exist, but they're very rare. Very rare. All right, Michaela.
Is the triple bond the strongest one?
Yes, triple bond is going to be the strongest. Think of it as like 3 sets of hands holding, you know, like at 3 bonds instead of just 1. So that is the strongest. Zane.
It was the triple bond thing. Sorry, I just
Oh,
stuck my hand down.
Okay. Yeah. Since they have 3 shared pairs, they're going to be stronger than single or double. All right. So we went over ionic bond. That's where one gives its valence electron to another one or more, gives it away. It's really strong because it's like a strong magnet that's stuck together, but they're not attached to one another. They're not glued together the way covalent bonds are. Covalent, they are sharing those electrons. They're both holding on to those electrons pretty tightly. So that keeps them together, but it's not quite as strong as an ionic bond. We'll get to metallic in just a second. But I want to talk about the hydrogen bonds that we have right here. So this kind of bond, the fourth kind of bond, happens between elements that are that have these hydrogen bonds. They're not ionic, they're not covalent, they're altogether different. They're much weaker. An example of this would be in water. Water molecules form hydrogen bonds with other water molecules. All right, so now we get to where the negative and the positive of a water molecule matter. Remember, water is polar covalent. That means it has a slight negative end and a slight positive end. Well, this slight negative end right here is attracted to the slight positive end of another water molecule, right? They want to stick together. They want to stick together kind of like weak magnets. They do stick together, but not very strongly. All you have to do is add a little bit of energy, like heat on a stove, and those hydrogen bonds can break. So if we've got water and we put a little bit of energy into it by boiling the water, those hydrogen bonds will break and water can go up into the air. So hydrogen bonds are not as strong as covalent bonds. Right here, these are covalent. We often draw them like a dotted line to show that they're not quite as strong, but they're strong enough, right? They do a good job of keeping water in the ocean. They do a pretty good job of keeping water wherever you need it to go. When you pour a glass of water, that molecules don't just float up into the air. So the hydrogen bonds are good enough. Now, if it wasn't for that hydrogen bond, all the water molecules would just float everywhere all by themselves. We wouldn't have liquid water and we wouldn't have ice. So that hydrogen bond is what helps these water molecules to stay together. All right, let's review all of this with this little Tim and Moby movie. I like Tim and Moby.
All done? Dear Tim and Moby, how do hydrogen and oxygen stick together to make water? Atomic glue or something? From Tabitha. Actually, she's not that far off. Atoms do tend to stick together, almost as if they were glued. If they didn't, there wouldn't be any visible stuff. Just a bunch of microscopic atoms floating around by themselves. Whoa. But atoms like to stick together, and the reason has to do with what's inside them. Atoms are made up of three basic particles: positively charged protons, negatively charged electrons, and neutrons, which have no charge. Protons and neutrons clump together in the center of an atom, forming its nucleus. Electrons whiz around the nucleus at different distances, which we call shells. Oh, shells aren't really perfect circles. This is just a simple model. In reality, electrons orbit the nucleus in three-dimensional patterns called clouds. But the circular model helps us see that each shell can hold a certain number of electrons. The first shell, closest to the nucleus, can hold 2. The second shell can hold 8 electrons, while the third shell can hold up to 18, and so on. And this is where things get sticky. Sticky. The number of electrons in an atom's outermost shell control how reactive, or likely to bond, it is. When the outer shell is completely full, the atom is inert, meaning it will resist bonding.
Get lost.
It helps to think of atoms as wanting to be inert, so they try to gain or lose electrons to reach a stable number. Well, take water. It's made of 2 hydrogen atoms and 1 oxygen atom. As you can see, hydrogen has 1 electron in its outermost shell. It would love to have 1 more, since 2 electrons would fill that shell up. Oxygen has 6 electrons in its outer shell. Since the second shell can hold 8 electrons, oxygen is looking for 2 more. So, oxygen shares a pair of electrons with 1 hydrogen and another pair of electrons with another hydrogen. Now all 3 atoms are stable.
Yay! Yay!
This sharing of electron pairs is called a covalent bond. No, wait! You know, every week it's the same thing. I teach you something cool, you shoot a laser beam out your finger, and I get in trouble. Well, not this time.
All right. Any questions about those kind of bonds? All right. Tomorrow you guys are going to be reading about another kind of bond. You'll be reading about metallic bonds. So if you haven't gone ahead in the lessons, that'll be tomorrow's lesson. I want to talk about metallic bonds. These happen in the metals. Metallic bonds occur among these metal atoms. So ionic bonds are going to join metals to nonmetals. Metallic bonds join a bulk of metals together. So like think of a sheet of aluminum foil or a copper wire. Those are both places where you can see metallic bonds working, and they're actually really cool. In metals, you can think of a bunch of atoms that all have electrons from all the atoms swirling around all of them. So the electrons move from one atom to another pretty freely. So you can think of them kind of as like a sea of valence electrons that move around between all the different atoms, kind of like in this picture here. And only imagine that these little E's are moving all around. They're moving everywhere. So the electrons all switch valence shells with neighboring electrons. Doesn't make them ions, because when they give one up, they're gaining one. So they're not ions, they're atoms. The electrons are not shared like in covalent bonds. They're not given away like they are in ionic bonds. They're not gained like they are in ionic bonds. They just simply swirl around in that sea of valence electrons. They're pretty cool. Pretty cool. I'd like to see that in reality. All right. Any questions about bonds and the 4 kinds of bonds that we have before we move into talking about chemical reactions? So this will be an introduction to what's coming. All right. Recap. What are the 4 kinds of bonds? Mel?
Hydrogen,
Hydrogen.
ionic, metallic, and covalent.
Excellent, excellent. Which one involves giving away an electron to another atom? Josiah?
Ionic.
Ionic. Which one involves sharing valence electrons? Matt?
Covalent.
Covalent. Excellent, excellent. Very good. And which one of the covalent bonds involves one of the atoms pulling the electrons a little closer to itself? Michaela?
Polar.
Polar. Excellent. Polar covalent bonds. Very good. All right, now let's talk about chemical reactions. So what happens in a chemical reaction? How is it different than a physical reaction? So think about like cutting something with scissors or melting water. That's a physical reaction. Something different happens when it's a chemical reaction. What is that something different? Josiah?
Sometimes it involves breaking compounds and breaking atoms into separate atoms instead of being a compound, or even can involve switching, sometimes it can involve destroying atoms altogether and like tearing electrons off them.
Okay, be very
Or
careful with
moving.
your wording. Remember, matter cannot be created or destroyed. So we don't ever destroy atoms, right? We don't
I mean,
create
like
them.
tearing
That's
the-
the law of conservation of mass. We can take them apart and put them back together. Jose, just like you do with your Legos. When you make a Lego structure and you want to make a new one, you take it apart and you remake it into something else. Well, the same thing happens in a chemical reaction. Atoms rearrange themselves to form something altogether new. This is the difference. In a physical change, nothing new is made. You still have the same thing you had before. In a chemical change, something new is made. That is always true. Always, always, always. All right. What question can we ask to determine if a reaction is physical or chemical? Josiah?
I think it's like production of different things, like a physical change will produce isn't it like light and heat? Or is that the way?
So not physical changes. Physical changes don't usually produce light and heat. That would be from a chemical change. But the question that I can ask to know if something was physical or chemical is, do I have something new? Did I make a whole new product? Did I take it apart, rearrange those atoms to make a brand new molecule or a brand new compound? Or do I have the same thing I started with? When I have ice and ice melts, I still have water molecules. I just have them in a different state. They've changed phase. They're not solid anymore. Now they're liquid, but they're still water molecules. When I burn something, I have something completely new. I've taken apart the atoms that made the wood, and now those atoms have rearranged themselves to make carbon dioxide, water, and the ash that's left when you burn a fire. All right. Now, what happens to the physical and chemical properties of a substance after a chemical reaction has happened? Once again, the answer to that is we have something new. What happens to things? It's something new. In a chemical reaction, the products that form are completely new substances. Now, sometimes you'll read these words, reversible and irreversible. It's important to remember, you can't say physical are reversible and chemical are not. That's not true, because there are some physical reactions that you can't reverse. Like this one. You drop this glass on the floor, you can't undo that, right? You can't put that back together so that it looks exactly the same. We didn't form anything new. We didn't take the atoms apart, from the molecules and build them into new molecules. Nothing new was formed. So in that case, it is irreversible, but it's still a physical reaction. And sometimes there are chemical reactions that can be reversed. Usually, in order to reverse a chemical reaction, it takes another chemical reaction. But just keep in mind that these two words right here, they don't necessarily go for, one or the other. All right. Now, there's a lot of examples that we can use of these different kinds of reactions. I like using water. I always think of water because it's something we know. I think water is an easy example. Now, water can be broken down into hydrogen and oxygen gas. We saw that a couple weeks ago when I showed you that experiment where they did the battery underwater and we got hydrogen and oxygen out of that water. But hydrogen and oxygen can also combine to form water. So both of those are chemical reactions, and the reaction can move in both directions. There are reversible chemical reactions. Take a look at this. There's some more examples. We start with just nitrogen, we add just oxygen, and we end up with nitrous gas. That's a chemical reaction. But look, see these arrows right here pointing in both directions? That means it's a reversible reaction. It can go in both directions. Hydrogen and iodine make hydrogen iodide. Nitrogen and hydrogen make ammonia. Those are examples of reactions that can go in both directions. So just be careful with that. Now, you'll hear these words, reactant and product, a lot in the next couple of weeks. So take a look at the arrow right here. This word means yields or reacts to become or something like that. I'm sorry, Matt, I didn't see you. Go ahead.
So with the experiment of like separating water into oxygen and hydrogen, if I took that and when they went up into the tubes up at the top above the cup, if I let the gases go into like a chamber of some kind, like a glass test tube or something, but they're both present, would it turn back into water?
Possibly. It's also possible that while they're in those separate containers, it's actually more likely when they're in those separate containers, they're bonding to themselves. So when you're releasing them, you're releasing individual oxygen atoms and individual hydrogen atoms. They don't like to be separate. They want to be bonded to something. They're probably going to bond to each other and form an O2 molecule and an H2 molecule, in which case now they're stable, so they're not going to react. Yeah, excellent question. All right, so look at the arrow right here. The elements or molecules, whatever is on the left side of the arrow or the side away from the point, those are going to be called the reactants. They go in to a reactant. They react. The ones that are on the outside are called products. On the right side, sorry. Those are called products. So these react to form this product. All right, so you can think of it this way. Reactants react to produce a product. So table salt is another one that's pretty easy to understand. We use table salt all the time. We have sodium plus chloride reacting to make sodium chloride. Now, if you look at this right here, how many chloride atoms are there on this side of the equation? 2. How many are there on this side of the equation? How many chloride atoms are on this side? Only 1, right? 1. So this is not what we call a balanced equation. In order to be balanced, we have to have the same number of all the atoms on both sides. So anybody know why? Why do we have to have, when we write an equation like this, why do we have to have the same number of atoms on both sides? If we don't, we're violating some kind of law. What kind of law are we violating if we don't? Remember the law of conservation of mass? If you don't have it balanced, you would say to yourself, oh, where did this other chloride go? It must have been destroyed. We know that doesn't happen. They're not created or not destroyed. So we have to balance this chemical equation. And when we write this equation, to help us understand it better, we can use letters and symbols like this, and numbers, letters and numbers like this. And this right here is called a chemical equation. We'll get into more of that next week. So remember our law of conservation of mass. This is really, really important. Matter cannot be created. It cannot be destroyed. We can't start with nothing and end up with an atom. We can't start with nothing and end up with a molecule. We have to take existing ones apart and remake them into something else. And we always have to have the same number on both sides of an equation. Here's a little cartoon. The law of conservation of mass. How do you not know that mass is neither created nor destroyed? All right, back to this again now. Remember that reactants react to produce a product. So when 2 sodiums, right here, 2 sodiums react with chlorine gas. Now we've got 2 sodiums and 2 chlorides on this side. We're going to end up with 2 sodium chloride molecules. That's balanced. We have 2 sodiums over here, 2 sodiums over here, 2 chlorides over here, 2 chlorides over here. This is a balanced reaction. These are the reactants. They go in. These are the products. They come out. Reactants react to produce a product. So just by adding those 2's right there, we end up with a balanced equation. Once again, looking at this here, the substances to the left of the arrow, so right over on this side, those are the reactants. They go in. The products come out of the reaction. So these sentences, we call them chemical equations. So how many oxygens are there in the top molecule? Well, let me get this on here. There, right there. So take a look at the top right there. This top equation right here. How many oxygen molecules are there? Molecules. Remember, a molecule is there's one. There's an O2. Oxygen likes to bind with itself. Oxygen really doesn't want to be alone. So it bonds pretty quickly to something. Right here, it's bonded to itself. So that's a molecule. If it was just an O, it'd be an atom. But it's an O2, so it's a molecule. So there is one oxygen molecule. So the molecule has 2 oxygen atoms bonded together. Now look at the one down here. How many oxygen molecules are there in that second equation? 3. There are 3. We can see right here. There are 3 O2 molecules, right? 3 molecules that have 2 oxygens in them. All right, look at the sulfur. How many sulfurs are there here in this one right here? There are 2. Exactly. So see how this is down lower? That tells you how many of those are in a molecule. When the number's in front, it tells you how many molecules you have. So we have 3 O2 molecules. We have 2 S atoms, right? All right. Now, let's hold on just a second. I want to see here. Oh, we're out of time. All right. So we'll end with reactants react to produce a product. The reactant goes in and is changed. The product is what comes out. Back to the Lego example, the reactant would be the piece you start out with. You start out with a boat. You take all those pieces apart and reform it into a farm. The boat was the reactant. The farm is the product. You take apart all the Legos and rearrange them into something else. And we're going to stop there and we will pick up a little bit where we left off next time. Anybody have any questions? All right. Hopefully this little review is helpful. This is kind of important as we go into the next couple weeks that you understand what those bonds are. So if you feel like you're still a little shaky on what the bonds are, go back and read that lesson and then contact me if you need more. Okay?
All right. Bye.
Have a great week,
Thank you.
everybody.
Bye.
Great to
Thanks.
see you.
Bye.
Bye.
Thank you. Bye.
Bye.